Welcome to the Predictive Analytics for Marketing course. My name is Dr. Ash Power, and this is lesson 3. In this lesson, we are discussing relationship and distribution. Now, in the previous lesson, that was 3.1, we covered the covariance and the correlation. Now, the correlation that we discussed was a Pearsons correlation. There is another type of correlation that exists in statistics, which is called rank correlation, which is also called Spearman correlation. So now this is lesson 3.2. Here we are going to discuss the rank correlation, which is also called Spearman correlation, and also we will discuss another topic which is called partial correlation. So this is the outline of this lesson. We are going to cover the rank correlation. Rank correlation is also called Spearman's correlation, and the reason why it is called rank correlation is because we do not do the correlation between the numbers, but we do the correlation between the rank of those numbers in the set. So rank correlation has a very wide application in sports analytics. Next, we are going to cover partial correlation. Partial correlation is computed when there are three variables in a model interacting with each other. We need to find out what is the real correlation between two variables by removing the effect of the third variable. The third variable sometimes is called lurking variable, and whenever a third variable is present in a model, is going to skew the results. So we need to find out a way by which we can remove the effect of the third variable. And this correlation is called partial correlation when the effect of the third variable is removed. Partial correlation is also used very heavily in sports analytics. So we are going to cover basically these two topics in detail. So now let us start with the rank correlation. As you would recall, in the previous lesson we covered the Pearsons correlation. Rank correlation is different from Pearsons correlation. In rank correlation, we compute the correlation between the rank of numbers. Rank correlation or Spearman correlation was invented by Charles Spearman almost 100 years back. So just to honor him, we also call this as Spearman correlation instead of rank correlation. So just for review, let us first look into the Pearsons correlation that we covered in the previous lesson. So as you can see, R is my correlation, and R is x minus x bar multiplied by y minus y bar, where x bar and y bar are the means, and then we sum up all these numbers for every observation divided by the number of observations minus 1, and again divided by sigma x and sigma y, which are the standard deviation of x and y. So let us take an example. Here we have club head speed and the distance. As you would recall, we can compute the correlation, and by default this correlation is called the Pearsons correlation. So as you can see, the correlation between these two set of variables, which are the club head speed and the distance, is 0.9386. So now let us look into the Spearman's rank correlation. We have the same data as we saw in the previous slide while computing the Pearsons correlation. So now let us look into these two variables. Here we have two variables as club head speed and the distance. So now let us look into the club head speed and now rank these numbers. We can rank them from lower to higher or higher to lower. It doesn't really matter. If we choose to use lower to higher, then both variables, which are club head speed and distance, should follow the same order. So let us start here with lowest to highest. And even if we choose the order to be from highest to lowest, the answer will come out to be exactly the same. So let us start with club head speed. Now, which is the lowest number in this case? It is 99. So 99 will get rank 1. Which is rank number 2? It is 100. Now 100 is appearing in two places, so we give 2 and 3 ranks to both the numbers. Then number 4 is 101, number 5 is 102, number 6 is 103. Now for numbers 7 and 8, again we have two numbers which are 105, 105. So here we are going to do a rank average. It means when the rank of two numbers are the same, then we split the ranks. So as you can see now that we have two numbers which are 2 and 3, and both of them were 100. So we are going to compute the average of these two things. So 2 will be going to change to 2.5, and 3 is also going to change to 2.5. Then again on number 105, we have two places. So here, so we have given the rank of 7 and 8. Instead of giving the rank of 7 and 8, now we are going to give the rank of 7.5 and 7.5. So here are my ranks now. Then we take the second variable, which is distance, and again rank it. As you can see, which is the lowest number here? 257. Second highest is 258. Third highest is 263. Then we have 264, 266, 274, and then after that 275 and 277. Here we don't have two numbers with the same rank. So here we don't have that problem. So we don't have to compute the averages here. So now we have computed the ranks. Now we are going to compute the correlation between the ranks of the data. So now let us try to compute the Spearman rank correlation. The symbol for Spearman's correlation is R with a subset of small s. S stands for Spearman. The formula for Spearman correlation is 1 minus 6 sigma di square. Di square is the difference of the rank square divided by n multiplied by n square minus 1. So n in this case is the number of observations, which are 8. Now let us try to compute the value of di square. As you can see, now I have a club head variable which I'm going to call as x, and the distance variable is y. Then I enter my ranks that we computed before in the previous slide. Now as you can see in my column D of my spreadsheet, I have my rank x observations, which are 2.5, 5, 6, 4, 7.5, 2.5, 1 and 7.5. Ranks of y observations are 1, 4, 6, 5, 8, 3, 2, 7. Then we take the difference of these ranks. So 2.5 minus 1 is 1.5. Now let us take the next number, which is 5 minus 4. That is 1, and so on and on. So we compute basically x minus y. Then we take the square of these differences. So 1.5 becomes 2.25, 1 becomes 1, minus 1 becomes 1, minus 0.5 becomes 0.25, and so on and on. Then we add up all these squares, squares of the differences. So if you're going to add these numbers up, they come out to be 6. Now we can compute the Spearman's correlation. The Spearman's correlation is going to be 1 minus 6 multiplied by di square. Di square we have just computed to be 6, and sigma di square is 6. Since we have 8 observations, so we divide this thing with n multiplied by n square minus 1. So the denominator will become 8 multiplied by 8 square minus 1. Now from here we can compute the Spearman correlation, which comes out to be 0.928. So the Spearman correlation comes out to be slightly lower than Pearson's correlation. So now let us try to understand what is the difference between them and when should we use the Spearman rank correlation. Now let us look into the difference between Pearson's and Spearman rank correlation. Both of them are going to vary from +1 to -1, and both determine the strength of the relationship between two variables. The basic difference between Pearson's correlation and Spearman correlation is that Pearson's correlation measures the linear relationship, whereas Spearman's correlation measures the monotonic relationship. Next, we are going to see a few examples where you will see that Pearson's correlation will be slightly different from Spearman's. So Spearman's correlation indicates that as long as I'm increasing the value of x, and if y is increasing, may not be linearly, But as long as y is increasing, the correlation is going to be 1. So that is the basic difference between Pearson's correlation. What we have is that if I increase the value of x and the y value also increases linearly, the word linear is very, very important here. Then of course correlation comes out to be 1. So that is the basic difference between these two correlations. The Spearman correlation has a lot of applications in sports analytics. Now let us look into this difference again. In a case of a Pearson's, when one variable increases, the other variable increases by a consistent amount. The word consistent is very important here. Whereas in Spearman correlation basically measures the monotonic relationship. When one variable increases and the other variable also increases by a non-consistent amount, the value is going to be 1. So y does not have to change linearly. Y can change as long as x is increasing and y is increasing. That's all it matters, because we are only interested in the ranks, not the actual numbers. So now we are going to see a lot of examples of Pearson's correlation and Spearman correlation. So this is my first example, and here you can say that I have a linear relationship between x and y. So here x values are increasing and y values are also increasing. This whole function is linear. So in that case, Pearson's correlation will be 1 and the Spearman correlation will be 1. Now this is another example. Here the x values are increasing, but y values are not increasing in a linear fashion. So the Pearson's correlation is 0.977, which is our standard correlation. But the Spearman correlation is still 1, because as long as y values are increasing as the x values are increasing, then the Spearman correlation will come out to be +1. So Spearman correlation only looks whether the ranking remains the same or not the actual values. And that is the basic difference between Pearson and Spearman correlation values. Now suppose if we have this type of a data, and as you can see that as the x values are increasing, the y values are coming down, but not linearly. So the Pearson's correlation is minus 9.165. But the Spearman correlation is still going to be -1, because as the x values are increasing, y values are decreasing. And that's all it matters for the Spearman, because the ranking of the data elements of x and y remains the same. So in that case, Spearman correlation is going to be -1. Now I have one more example. Here you can see that the data is increasing in a non-linear fashion. So Pearson's is going to be 0.9, but the Spearman again is going to be +1. Now let's take another example. As you can see, it is a linear decline. So Pearson's correlation is -1 and the Spearman correlation is also going to be -1. So now we have seen these 5 examples which shows the difference between the Pearson's correlation and Spearman correlation. Now let's take the last example, and this particular data element is nothing but a parabola. So it is a quadratic function. Since it is quadratic function, Pearson's correlation will be 0. And Spearman's correlation will also be 0, because as the x values are increasing, y values are coming down first and then they are going up. So in that case, there is no correlation between x and y values. So whether you use Pearson or whether you use Spearman, both correlation values are going to be 0. Now let us look into the examples in sports where Spearman rank correlation is used very heavily. As you know, in swimming, ice skating, gymnastic sports, there are a bunch of judges. Usually sometimes there are 3, 5, 7 or 9 judges. They always take odd number of judges because in case of a tie, the decision can be resolved. These judges give points to athletes based on their performance. So Spearman correlation can be used to compute how well judges agree with each other. In really important sports like Olympics, you're going to see that the judges have a very high Spearman correlation. It means that most of the time, judges do agree with each other in terms of ranking. Every judge has their own scale of giving the points, but the ranking pretty much remains very consistent. If the Spearman correlation is very low among the judges' scores, then someone can question the integrity of the judges. Ranking in this case is important. So what important is the relative points. So relative to other athletes, how many points somebody got. So in this case, rank is which is important. Now we are going to take some examples and we are going to compute the Spearman correlation of the points given by the judges. Now suppose we have 4 athletes and we are going to give them a name of A, B, C, and D. And we have 2 judges, and these judges are X and Y. So Judge X basically gives these points to athletes A, and suppose these points are 4, 3, 2, and 0. And then Judge Y gives on a different scale, and these points are 5, 4, 2, 1. So as you can see, the best of X is 4, whereas the best of Judge Y is 5. It doesn't really matter what number you give, but as long as you evaluate all the other athletes on the same scale, that's all it matters. So now let us compute the Spearman correlation. In this case, the rank, as you can see, of both X and Y judges are 1, 2, 3, and 4. So in this case, the difference is going to be 0, and Spearman correlation will come out to be 1. Spearman correlation 1 basically indicates that there is a perfect agreement between these 2 judges. And whenever we have a very competitive sports like Olympics or any other sports which has been played at the national or at the international level, you're going to find that the Spearman correlation of the judges' score is usually very high. Most of the judges usually have the same way of judging the athletes. But suppose if the Spearman correlation happens to be very low, then that is going to cause a lot of problems. So next we are going to see an example where we will see a perfect disagreement. Now this is our next example, and here we have again same 4 athletes A, B, C, and D, and we have 2 judges X and Y. Now Judge X basically gives a point of 1, 2, 3, and 5 to these 4 participants, whereas Judge 5 gives 5, 4, 1, and 0. Now as you can see that if first of all let us compute the rank, and then after that if you compute the difference and then add the whole thing up, it comes out to be 20, and the Spearman correlation comes out to be -1. -1 indicates that there was a perfect disagreement between Judge X and Judge Y. So judges X evaluation skills are very, very different from Judge Y. Most of the time this sort of a thing does not happen. But if it does happen, then the whole system of evaluating the players or athletes become a sham. Then people don't have much faith in the judges. So this is the way by which we can find out by computing the Spearman correlation how much agreement is there between the scores given by the judges. Now let us look into the third example, that is the last example. And here we have 5 athletes and the scores given are by Judge X is 2, 3, 5, 1, 4. And the scores are given 1, 4, 5, 2, and 3 by Judge Y. Now let us compute the rank of X and rank of Y, and then compute the difference, square the difference, that comes out to be 4. And now if you compute the Spearman correlation, it is 0.8. So 0.8 is not that bad. Most of the time in the real world data, you're going to find it will be somewhere around 0.7, 0.8, 0.9. That should be a normal case. But if it is below that, then you don't have much faith in the judges because they have so different in ways by which they are judging the athletes. So this is one example in sports where Spearman correlation is used very heavily. Now let us look into the second topic of this lesson, which is partial correlation. So the partial correlation exists whenever there are 3 variables and all 3 variables are interacting with each other. So in these kind of a cases, usually we have one variable as the lurking variable. So let us take a very specific example. Now suppose if we take the crime data, you will notice that the air conditioning bill goes up as the crime rate goes up. So it means that that if more people are using air conditioning, it means they are consuming more electricity. The crime rate is going up. So of course this sounds pretty weird when you just look it on the surface of it, but that thing is absolutely true. If you look into the data in those cities where we have a lot of snowfalls, the air conditioning bill and also the crime rate are highly correlated. So now someone may scratch their head and say that, oh, how come these two variables are very highly correlated? And the reason why this thing is happening, because the temperature is playing a very important role. When the temperature goes up, of course, we all know the air conditioning bill will also going to go up. But when the temperature goes up, the crime rate also goes up, because in those cities where it snows quite a lot, which are the northern part of the United States, where it's so cold that most of the criminals don't go out to even commit crime. So that is the reason why in summer usually you're going to find more crime. So somebody can argue that, hey, as the temperature goes up, air conditioning bill goes up. So if we are going to reduce our air conditioning, the crime rate will come down. Of course, this thing is absurd. This thing that does not make any sense. But if you include the temperature I mean, as a third variable, then of course everything makes sense. So basically, correlation does not mean causation. It means if there is a correlation exists between two variables, it does not mean the causation. It means that that when the air conditioning bill is not the cause for the crime. So that's what basically it implies. Now we have to compute the partial correlation between the air conditioning bill and the crime by removing the effect of temperature. And that is called the partial correlation. I mean, how to compute the correlation between the air conditioning bill and the crime rate by removing the effect of temperature. So that thing is called partial correlation, and that's what we are going to define next. Suppose we have three variables. These variables are shoe size, reading ability, and age. Now suppose we have data in which we have some small children as well as some adults. So you're going to find that there is a very strong correlation between the shoe size and the reading ability. And as you can see, if you compute the Pearsons correlation between these sets of data, we're going to get the value of 0.8. So does that mean that bigger your shoe size is, the better you can read? Of course, this thing sounds pretty absurd, but we can prove it from the data that larger the shoe size, the higher would be the reading ability of the person. So this correlation actually is a false result. And in the next slide, we are going to find out exactly what is happening over here. If you're going to look into this data more carefully, you will see that there is a third variable, age, and there is a strong correlation of shoe size and age. And of course, it makes a lot of sense, because as the person grows or as the person ages from child to adult, the shoe size of that person is going to increase. There is also a very strong correlation between shoe size and age. Similarly, the reading ability and the age are also very strongly correlated, because as we all know, kids don't read as well as adults. So again, as you age, your reading ability is also going to increase. So there is this third variable, which is called the lurking variable. That thing is playing a role in this model. So the thing here is this, that as people grow older, their shoe size increases as well as their reading ability increases. But there is no direct relationship between shoe size and the reading ability. Once we have the raw data, the computers or these models can compute these correlations without understanding the semantics of the data. Someone may erroneously compute or reach to this conclusion that bigger the shoe size, the higher would be your reading ability, which of course is absurd. What we need to compute is a role of age in this model. We are going to now find the correlation between shoe size and the reading ability by removing the effect of age. So that correlation between the shoe size and the reading ability by removing the variable age would be the real correlation, and that correlation is called partial correlation. So now let us try to compute the partial correlation. It is defined as follows. Now suppose if I have variable shoe size is x and my reading ability variable is y. The correlation between x and y by removing the effect of age is written as rxy dot z, and this means correlation between x and y by removing the effect of z. So partial correlation, which is rxy dot z, is equivalent to, or it is defined as, correlation between x and y minus the product of correlation between x and z and y and z divided by square root of 1 minus the correlation of xz whole square multiplied by 1 minus r, which is the correlation between y and z whole square. So this is the number that we are really after. This would be the true correlation between shoe size and the reading ability. Now we are not going to derive this formula. The derivation of this formula is being given in many books on statistics. But we are going to take this formula result and then going to compute the value of the correlation between shoe size and the reading ability by removing age in the next slide. So now let us compute the correlation between x and y by removing the effect of z. So again, we just plug those numbers in and we know the value of xy, xz and yz correlation. Once you plug these numbers in, we get the value of 0.152. So that is pretty much we expected. There is no correlation between shoe size and the reading ability. So age is the third variable that is playing a role in this model. That is the reason why we see a strong correlation between shoe size and the reading ability. So in sports, we face many times these kind of situations that we have a third variable is going to play a role. So we have to remove the effect of the third variable to compute the real correlation between two variables. So this is the final conclusion. The correlation between shoe size and the reading ability was 0.8. But if you remove the effect of z, which is my age variable, it basically drops down to 0.152. So age variable is inflating, or I should say strengthening, the relationship between shoe size and the reading ability. Most of the time, the third variable is always a time factor. In this case, of course, we have age. And we are going to see a few more examples later on where time usually plays a very important role. So if you really want to find out the relationship between two variables, you have to remove the effect of time and then see the true relationship between two variables. So that is the end of this lesson. In this lesson, we cover two items. The first one is rank correlation. Rank correlation is also called Spearman's correlation, and here the ranking of data is important, and this correlation method is used in many places in sports. One place where it is used very frequently is to see how much amount of agreement is there between the judges who give points to the players in sports like gymnastics, swimming and ice skating. Besides that, rank correlation is also used in many other places in sports. The second thing we looked into is partial correlation. Partial correlation is used in those places where we have the lurking variable or the third variable that plays a role in computing the correlation between two variables. So if you have two variables, then it shows some high correlation. Then you have to apply your own common sense and see if there should be a high correlation or not. And if you suspect that there should not be a correlation, look for that lurking variable or the third variable. If you can find it, remove the effect of the third variable from the correlation. So this is also used many places in sports. It is good to understand the rank correlation and also partial correlation, because both of them are very useful metrics used in sports data analytics.